I will put that one here, and I will start to transmission that one for YouTube channel now. I'm sorry. Hello everyone, my name is Fernando Oliveira. I'm here in the channel in Brazil, called Doutor Fundição, but in English it's Dr. Foundry, Dr. Casting. And I'm here to talk with the new test for chemically bonded sands with the professor Sam, who stay with me here. It's a pleasure to me start that program with him. And good afternoon, doctor.
Good afternoon.
Oh, it's a pleasure to me. Stay with you here in my channel. It's a pleasure. It's very. I'm very. It's a very good time to me now to watching your lecture now about that important subject. And first of all, I wanna congratulate you for your work with that theme, that topic. It's very important. The quality control, it's in molding, it's pretty important. It's very important in my opinion, because I'm specialized in foundry process, and if you don't have a good mold, you have problem. And to me, it's very important your job, your I'm sorry, I'm very I'm not so okay. And what you prepare to us today, please?
Well,
I'm sorry. First of all, please introduce yourself to my audience, please.
Okay. Let me share my screen. Is that all right?
Okay.
Right. Okay. Good afternoon, everyone from Kalamazoo, Michigan, and Western Michigan University. It's my honor, my privilege, and a pleasure to take part in metal casting activities. And thank you, Dr. Fundição, for giving a great opportunity to talk about some research and development work that has gone on here at Western Michigan University on new tests for chemically bonded sands. And now these tests have been adopted as standards at the American Foundry Society, or the AFS, and it is being used in industry for process control and also for data analytics as part of Foundry 4.0 strategies here in the US.
Okay. So guys, I really appreciate the opportunity to being here. And now I have special thanks to do to Carlos Freire, that will be here with us, and Carlos Freire and the others one who stay with us now. Okay, Professor. Now we have the agenda, okay, to that event. The other one is that event was transmitted by Zoom and on the YouTube channel in Portuguese, simultaneously in English, here in English, and the other one in Portuguese. If you want, you can choose your sound. Para você que está aqui em português, pessoal que chegou agora aqui no nosso link, muito obrigado pela sua presença. E basta você clicar aí na parte de baixo em intérprete e colocar em português, que você consegue ouvir o áudio em português com o nosso tradutor, Fernando Roque, que nos assiste aqui, nos acompanha neste evento. Please, Professor, go ahead.
Okay, thank you. Okay, so for today's agenda, I will be giving some brief introductions and background relative to chemically bonded sands. And I want to spend a significant time on the why or the purpose for these chemically bonded sand tests. Certainly chemically bonded sands are going to be a little bit more costlier than other sand casting processes, certainly the loose or naturally bonded materials. And for that reason, we need to understand why a testing program might be important in a foundry. And then I'll spend some time showing you these new tests and then talking about a qualification strategy. What qualification means, it's a performance predictor. How does the materials that we use in molding handle the temperature, the chemistry, and the head pressure of the alloys that we're using? Oftentimes, our foundry professionals love to see the casting trials and how they relate to the actual tests that we're running in our labs. After that type of discussion, we will open a time for taking your questions and answer. So let me start by showing you a modern facility for chemically bonded sands, something that appears very organized as a department in a high production foundry environment to make very complex shapes with section thicknesses that can be less than 4 millimeters, as depicted by this water jacket core on the bottom of this slide. This type of molding, core making endeavor is the purpose of chemically bonded sands. Here in Michigan, our high production automotive powertrain castings using these technologies can produce these at very fast speeds for complex designs and near net shape casted parts. However, the typical control charts for process control in these sand casting processes show us that the process variability, the total variability, is equal to the process variability plus our measurement variability. Process variability is made up of the three important areas in foundries: the variability from filling, the variability from melting, and the variability that could come from molding. The melting and filling processes are usually consistent, as depicted on the right. These control chart slides show that the consistency offers low variability in the data, and that is normally distributed in such a way that we could predict what's going to happen next in fill or in melt technology. These technologies lead. However, when we look at the same ideas for the control chart in molding, sand control data reveals higher variability. There is abnormal data patterns that result almost as if the process is being rigged so that we push the data into the customer's specification. And this particular trend over time has led us to look at the major sources of quality problems around sand casting, around molding technologies. Thus, I will give some background reasons why we are focused on the chemically bonded sand sites, remembering that the cost of this process for precision sand is going to be slightly more. But certainly there are requirements for Foundry 4.0. Today, the push is quality is a given. We have to have high productivity. And how do we make these casted parts without the touch of human hands? Well, we need the data from these chemically bonded sand tests to be the inputs for data analytics. These are important pillars for industry or Foundry 4.0 strategies. In addition, an important consideration is some of the metallurgical concerns. Where does the magic happen? The magic happens where the molten alloy meets the sand, and in this case, a sand binder system. If we can imagine that a recipe that has molten metal, it has ceramic media, and it has a polymeric binder or some other inorganic constituents. The point is, the chemical binder may give first. And if we don't have the stability needed there, it can be a concern for shaping the casting. But the point I ultimately want to make here is that that magic happens at the mold metal interface, and at the mold metal interface, there are thermomechanical, thermochemical, physiochemical, and thermophysical changes all happening at the same time in a very dynamic manner. AFS, the American Foundry Society, has many standardized tests documented in their mold and core handbook. Unfortunately, the mass majority of these tests are autonomous. They measure the properties in our sands mechanically or thermally or chemically. And for that reason, we don't get enough information from these tests. We need performance predictive measures for precision sand systems. We need to understand how these molding materials will behave against molten alloy. And for that reason, this idea of performance prediction is what we are deeming or referring to as the ideas for qualification. And I will share some of these ideas towards the end of my presentation. Ultimately, there are conundrums. These types of confusions are questions that could be redundant. So I'm going to try and answer them quickly based on some of the issues I've brought up. What do the numbers, what does the data mean from the chemically bonded sand test? Well, I am saying they're going to mean very little if we do not have livable variability, meaning if the variability in molding and process change is higher than mold, melt, and fill, they're not going to help us with our casting quality issues. What should we be measuring? Well, as I suggested, we need the thermomechanical, the thermophysical, the thermochemical properties. These dynamic properties are going to be new. When should we measure? Should we be measuring from our processes hourly, daily, weekly? My answer to that is that we need smart data. We need the digital data from the process in real time, and that should be happening at the line speed. Another question could be, where should we measure? Well, these measurements have to be translated, no matter if we're taking it from the mold, it has to be related to melt and fill. So at the end of the day, the process measures should be representative of measures at the mold metal interface. The purpose or why we have to do these precision sand testing for chemically bonded sands is that the quality process control programs are important for the customer. And quality first, casting defects. If there is a defect resultant from mold, melt, or fill, we have to account for the molding side. And today we will be talking primarily about the concerns around chemically bonded sands. And that is the characteristics of the chemically bonded sands are being altered from ambient to elevated temperature, and vice versa as that casting cools as well. The process control rationale is the quest for consistency, meaning we need to understand what this chemically bonded sand mold is looking like at 8 a.m., at 9 a.m., at 10 a.m. And as we go through our production day, we end work and we come back the next day, we need to make sure that we are consistent. That is the idea of control. The other aspect of why the chemically bonded sand testing is important is that there are changes in technology and sustainability happening in our foundries, in our metal casting facilities very, very quickly these days. We have new materials. These new materials could be coatings, sleeves, filters, the sand blends. Let me speak about the sand blends that we're using today. They are no longer just silica sand. Circa 2018, there were new laws in the US, and those laws are on the silica mandate that forces foundries that expose their employees to more than 50 micrograms of crystalline silica in an 8-hour work period. That is now a law that if the foundries are found breaking those regulations, they literally can be warned and then shut down. But because of that, we have several alternative media. These alternative media could be natural or ceramic sands. Along with these new materials in sand, we have new binders. The world is seeking greener and sustainable technologies. Our chemical binders are not just organic systems, they are inorganic systems, but certainly we are moving towards a sustainable green path in all of these materials, whether they are sands, whether they are binders, whether they are internal additives, these special chemicals that we put into the sand or onto the sand to give us some casting benefits. They also are things that are placed on the chemically bonded sand molds. In terms of technologies, we have to understand the test data, the test properties, again, mechanically, thermally, physically, and chemically, so they become input boundary conditions for the advanced engineering tools that we use, like the solidification simulation tools. But ultimately, an important technological challenge for us is to stop testing. And the reason why we need to stop testing is only because our metal casting facilities, like foundries, they don't make any money testing. That is an overhead cost. They spend money testing. So here are the technological implications for chemically bonded sand costs. We have to develop the processes for rapid mold development. Here in my state of Michigan, large automotive precision sand casting processes are using permanent molding processes or semi-permanent molding processes at line speeds of 60 moles or cores per hour. That's 1 per minute. That's pretty fast for this technology. And we can't make bad molds or cores. Why? It will increase cost very quickly. Secondly, the alternative molding media that I just mentioned, these ceramic sands and otherwise, are being used for our high-end casting processes. and the high-end chemically bonded sand processes. Certainly 3D printing technology is a chemically bonded sand process, and we must get that right the first time. Otherwise, if we destroy that mold, we now destroy the more expensive part of mold, melt, and fill. The traditional casting trials that we have been doing in the past in a trial and error fashion, we no longer can do business that way. We have to get this right from the advanced engineering tools like simulation and digital twinning, but we can't invest in the casting trials like Gertzmann and step cones. These take literally hundreds of kilograms of alloy, and they become expensive, unnecessary, redundant technologies, and we must find better ways. A little bit more on the ideas of the alternative to silica sand in our foundries. Certainly, the AFS has invested in research and development, and I have been part of that work circa the time frame of 2016 through 2018, where we studied, here on this list, I've listed them A through F, and the control media is silica sand shown in this table as G. We studied these in detail for a variety of casting processes. My comments today will be reflective only of chemically bonded sand technologies, but the media that the AFS were using in their studies were predominantly alumina and alumina oxide materials that were heat processed to sintering or fusion temperatures. And because of that, we will make phase changes in the material that will affect the material relative to sand, even if we are keeping the size, the shape, the grain distribution reasonably same. There can be some issues. I want to show you what these issues are and what we were studying. For example, the raw sands that we were studying, they change simultaneously during impact as well as abrasion testing. Certainly, the sands break down more from impact versus rubbing. And that's because the compounds that we form in the casting process. And some of these changes for these sands is not only due to high temperature exposure during casting, but after we've used these chemically bonded sands. I have mentioned they are more expensive granular media compared to silica sand, so we must recycle them. And in the reclamation process, they see more of this impact and abrasion due to thermomechanical reclamation. Certainly, the elevated temperature exposure of these materials changes their compositions, the compounds. They are naturally hard compounds, but the proportions of these hard compounds change as well. And certainly, these hard compounds are brittle, and when exposed to impact and abrasion, they change the distributions rather quickly. And the heat from these processes can also make phase changes and new compounds in the materials after reclamation as well. So at the end of this, what we found in that AFS study is there is no panacea. There is no cure-all for an alternative granular media, ceramic or natural, with the use of the casting process. We must qualify. We must find the performance predictor before we choose the granular media for the chemically bonded sand process. And then today, because of cost, we find in the foundry industry that they are blending these sands as well as using other additives along with the binders. So here I'm showing on this graph our standardized specimen, which is a dish-shaped specimen or cookie. That dish-shaped specimen is 50 millimeters in diameter and 8 millimeters thick. And here I'm showing one that is made up of primarily all silica sand. And then on the bottom left, it's one made up of a granular ceramic sand. And we could have a recipe that is 50-50 of the silica sand to the ceramic sand. We could have it where it's 80% silica sand, 20% the ceramic, or vice versa, 80% ceramic, 20% silica, or 60-40, 40-60, as the case may be, to study what are the thermal benefits, such as heat transfer, such as mechanical strength, mechanically, or any dynamic properties. They all change with blends. But the issue that the foundries are doing these are primarily to reduce their sand to metal ratio to save money, and also to lighten the weight of the cope for large size castings. Why? Because the bulk densities of the natural aggregate like silica sand is significantly different from our alternative ceramic sands. And for these reasons, for all of these reasons, qualification strategies for the chemically bonded sand molds and cores are necessary. Today, in the manufacturing process, we can have mass production strategies where every mold is the same in continuous manufacturing down to the end mold that we produce, or we could vary those molds in production with limited order, large scale production from processes like 3D printed or no bake technologies as well for chemically bonded sands. But we still have to ask the questions when we have to pour these castings in large quantities. Does the sand, in this case, the sand mold, we are representing the mold by a disc-shaped specimen. This cookie-shaped specimen, again, is a simple disc that is 50 millimeters in diameter, 8 millimeters thick. And we're asking then if these specimens, they vary mold to mold and core to core, because we like to produce them as we produce the mold and as we produce the core. A second question that we should be asking is, does the sand dish-shaped specimen vary casting to casting? And in order to answer this question, we are putting the dish-shaped specimen or the cookies inside of a mold, and we are wetting that the recipes for these different cookies at the same head pressure with the same metal chemistry at the same superheat temperatures. So we are getting that data. So that data goes into more sophisticated analytical tools that we need to employ for process control and ultimately the predictability of our processes for chemically bonded sands. With that type of background, I want to share now what some of these new testing methods are. This first slide, though, is to share a little bit more about a new standardized specimen. It is the cookie specimen pictured on the top right. Again, this specimen is nominally 50 millimeters in diameter and 8 millimeters thick. That's the specimen that we will be using with all of these new chemically bonded sand tests that I will be talking about. But I want to mention the other standardized approaches that exist and that are being used globally. Certainly, most people in the foundry industry are familiar with the dog bone specimen. And I have the dog bone specimen. From the dog bone specimen, we only get mechanical data. That is the problem. But that is not the only problem. This specimen has this narrow waist, we could call it. I like to call it the sexy part, but it sometimes doesn't always break there. It breaks up at the shoulder, It sometimes break lower down at the waist. And for that reason, we have higher variability test to test in the mechanical test. We have found that the Kit Kat bar, I'm keeping everything like food today. This rectangular specimen is an excellent type of specimen to get, again, mechanical properties, the shear, the modulus, the ultimate strengths and compression and tension are well understood in 3-point loading of the Kit Kat bar specimen, this rectangular bar. But again, with this specimen, we only get mechanical properties. And for that reason, we have modified the shape of the specimen to this cookie shape, because shape is a factor in casting. If you have complex geometry, we don't always understand the thermomechanics, and even the pure mechanics or the pure thermodynamics, much less for the thermophysical and thermochemical changes that could be caused. So shape is a factor. The cookie specimen is also easy to eject during a molding process, whether it's cold box, snow bake, or hot box technologies, or even we can print the cookie in the same build box during 3D printing. And these specimens are stress-free in these processes when we produce them. But most importantly is the idea of heat transfer. What if I put heat right at the bullseye, right at the center of the cookie specimen? It is easier for us to understand from an engineering standpoint how that heat radiates radially from that cookie, and how that heat transfers actually in that specimen as well. So we like the cookie specimen, but one important thing about the cookie, we like to get the data in a smart regime. Smart data means getting specimens that are representative from the process in near real time from the actual processes that we are using for chemically bonded sands. So representative process data is important. On this slide, I'm showing the new standardized dish-shaped specimen testing technologies: the thermal distortion, the hot permeability test, the fast LOI or loss on ignition test, the impact test that we use for measuring the retained strength on our sand, whether it's a newly developed chemically bonded sand, or after that chemically bonded sand has been exposed to heat, we can measure the retained strength to understand if we can shake out that casting from the chemically bonded sand mold. And then the ideas of the abrasion test is to tell us about the cure rates of the sand, and if in fact that sand system can withstand the erosive flow of molten metal going past it. So I will deal with each of these tests individually and share with you some video so you can better appreciate the procedures for the technologies around the chemically bonded sand specimens that we are using for the testing. So after we have tested a dish-shaped specimen, we can collect the residual for use in the loss on ignition test. And this is where we take that specimen and we take the weight before ignition and after ignition. The range of the mass change divided by the original mass brought to a percent is an indication of the LOI. And after the LOI, silica sand appears snow white after we have burnt off the binder. Today, we can run this test fast, inline. We can get that loss on ignition data that we would get from the AFS standard test. That test would take at least 3 hours to get the data. It takes 2 hours to to run, and by the time we cool down the crucibles and take the change in mass readings, it's about 3 hours before the foundry can use that data to tell if their sand binder systems are high, low, or anywhere in between. Today, we could run this test in less than 10 minutes by using an inline fast LOI testing technology that has been automated. This technology is available for working foundries, and it uses a computer data acquisition to control test temperature and duration, to collect and store the data. It plots the curves for mass loss versus time and temperature on the sand, and calculate the moisture content, the volatile chemicals, as well as the loss on ignition in a chemically bonded sand. And again, this type of data can be achieved very quickly today. Another chemically bonded sand test that is not so new is the permeability test. This is the ambient permeability test that has been modified. And we have a formula for driving the permeability number. I'm not going to get into the details of the formula, but what really is happening in this test is that we are forcing 2,000 centimeter cube of air through that specimen, and we are measuring the time it takes to displace that volume of air, and we relate that particular value to a permeability number that we calculate. But it's really a function of time. It's really the law of continuity. More importantly, if we could do this test hot, and that's what is new, will be the important thing. The inverse of the permeability test is to take a known compressed air pressure and place it against the specimen. That is called the MQI, or the mole quality index. This is also a standardized test at AFS, and this is the inverse of the permeability test. Again, to show you how that test would work, we would gasket a specimen, place it into a specialized specimen holder. That would allow, when we secure that specimen, the gasket to collapse around the circumference of the specimen and secure it, so that the air that we are passing through the specimen can travel in only one direction. So when we start the permeability test and we displace this air, we will get a permeability number. Again, it's just measuring how quickly we vent air through that specimen at ambient. And then we can run the mole quality index test with using the same specimen holder. And that shows an inverse relationship between the permeability number and the MQI. They are related. But more importantly is running that test hot. Why that is important is because, again, the dynamic properties of green sand during the casting process is where the magic happens. That sand, when it gets hot, the binder bridges changes, they soften, they collapse, or they vaporize. And because of that, the permeability number during a hot experience at the mold metal interface is a more important value for our advanced engineering tools and understanding the venting characteristics there. The disc shape strength test is an AFS standard for the disc shape specimen, and this particular test is just a mechanical test. We don't like this mechanical test very much because very few molds and cores fail in this compressive shear mode. Again, what I'm suggesting here is a mold and core that we use in the casting process. They do not experience compressive shear. So for a mechanical test, The new standardized test is the retained strength test, which is an impact test. And how this how this test works is that we support a cookie on a goalpost. It's a simple setup, like a rugby goalpost, and then we impact that specimen symmetrically. That particular idea gives us, again, the energy of how a core or mole could fail in shakeout. So if we have the energetics, the energy in joules, as we make this chemical binder system, and we understand that chemical binder system after heat exposure, and we can measure its toughness, then we can use the same energetics to develop our shakeout equipment for a sand binder system. And we have this test automated. We are developing this right now, but I have a video of the prototype equipment and the volume on, so you could see how we can set this apparatus up for an impact test, and how a cookie could literally fall in place from the production line. That cookie specimen would roll off the production line, fall into this, and we could impact that specimen, get the energetics, and that data could be, again, smart data that could be digitally sent forward for processing. Another new standardized test is the abrasion test that we look primarily for the cure of sand. This is basically the idea for an operator rubbing his or her fingers on the sand mold and core. So we have a ceramic ball, a hardened ball loaded with 200 grams, and that basically rotates 20 rotations as we draw by vacuum the debris at the curve, and that would reveal abrasion loss. We can measure the depth of loss, and that depth of loss is directly related to mechanical or other physical and chemical properties of the chemically bonded sand test. Again, it's a good indication for degree of cure on the specimen. The preeminent new test is that of the thermal distortion test, and because of all of these long words, we use the acronym TDT. It measures the expansion, contraction, the degradation experienced by a mold and core under the extreme heat and liquid pressure of the molten metal. Let me stress the importance of liquid. Again, when the casting is solidified, the load against the mold or core for the chemically bonded sand is just down in Z. But as we fill that casting with the liquidous hot metal, the thermomechanical stresses are important. And we understand what these liquid pressures could be all the way through solidification. And if we can express that through rho GH, we can develop testing that better subjects our chemically bonded sands to get real-time smart data. When I say real-time smart data, time series data about our chemically bonded sands. For example, here I'm showing you in the picture at the bottom left, a chemically bonded sand after we've taken a SEM or scanning electron microscopic shot to show you the binder bridges. I took this picture myself, so I know exactly what is happening. And at the heat affected zone from the thermal distortion test, we have sand losses as seen on the cookie. In this particular cookie, it's a urethane cold box specimen that showed that the binder pyrized in the darker colors. We lost sand at the crater. This particular image is the actual cookie, and it also shows a crack that has occurred after elevated temperature exposure. So if I took a magnified view, the SEM shot of that crack, I know where it is. So the same crack the magnification of that crack is right here. And if I look closer into that crack right here, right at this point, there is a sand grain with a binder bridge that I'm showing you in the bottom right photograph. There is that binder bridge, and this is the crater for that crack. If that crater is 1 or 2 millimeters, that's enough for liquid metal to penetrate. And the classic defects like veining, like penetration, we see on these cookies as well. We will show you the evidence of that. So the thermomechanical test of thermal distortion testing allows us to evidence expansions that can be depicted in oversized castings, as well as distortion or the displacement of the mold walls, the dilation of the mold wall, or the sagging of the mold wall, causing bending or thermal shock to that sand binder system that can lead to penetration, veins, or rat tails as a defect. In case you need to remember what those defects look like, I am showing on the left a rat tail or a vein. That is the classic defect that now some foundry operator has to do more than mold, melt, and fill. This has to be taken to the finishing room, and we have to grind away and machine this to satisfy the customer. Similarly, penetration is seen by the roughening of the casting as this raised demarcation. These are actual castings. We will show that if we have an inappropriate chemically bonded sand, we can find that due to a qualification regime. But to tell you more about the thermal distortion test, I am using this depiction to show you a hot surface that has a heated surface that is 20 millimeters in diameter. And we heat that typically to the mold metal interfacial condition of the alloy. So we can represent aluminum temperatures. In this case, I'm showing you the temperatures around a copper-based alloy, like a black brass or a bronze temperature. But we can get up to iron temperatures. Unfortunately, at this stage, we are limited to iron temperatures, and we are developing technologies around the hot surface to get to steel temperatures, but we're working on that. The other thing that we do on this test is that we support the cookie specimen on a gimbal. The support for that specimen is only 1 millimeter around its circumference or periphery. And then we load that. We load that specimen to represent the hot surface area against the symmetrical loading at the bullseye of this specimen to represent rho GH. That is the metallostatic head pressure from which we pour that casting from the pouring basin down to the parting line. That is the pressure we express during this test. So the specimen does not have to fail. This is not necessarily a destructive test. A cross-section of the loading of this specimen shows that the rotational surface is not the neutral axis, but is the interface of the hot surface that represents the molten metal and the specimen that represents the chemically bonded mold or core. And that specimen is loaded in a compressive tray mode, and that specimen is free to bend and to expand, and we monitor the changes to that specimen dimensionally and thermally, three-dimensionally. So we measure radially and axially the thermomechanical changes on the specimen. To show you the test setup, run this video. Oops, let me go back. Let's get this video to play. Okay, so this is the start of the test. This is a semi-automated test. So once you press the button on the computer, the test will start. It brings the specimen against a hot surface. We are measuring temperature on the backside and at the hot surface, so we can measure a thermal gradient. And you will see that the specimen that is 50 millimeters in diameter is radially expanding in real time. We measure the radial, the axial changes, and the heat transfer in this system in real time. That data is acquired so that we could develop the thermal distortion curves for the test for further analysis after the test has been completed. So the specimen remains intact after the test, and we could again run the impact test for retained strength or other tests relative to the chemical sand binder system that we are studying. Here is an example of that specimen before and after a test. This happens to be a urethane cold box type of specimen. It shows the heat affected zone, and it shows what happens beneath the specimen after we have blown away the loose spiralized sand and the crack fracture that typically would happen on the sand binder systems. Some of it is due to bending, but some of that crack propagation can happen by thermal shock. During the thermal distortion test, we know exactly what time and at what temperature the crack occurs and when these changes occur. This is the analytics that drives when that casting needs to freeze, because if that casting is still liquidous when there is cracks, when that hot sand has opened, literally that crack will close when that mold is left to cool. But in the liquidous state, that molten metal is picking up that crack to cause us defects. So we did a simple experiment where I will show you the longitudinal or axial displacement for a silica sand. This is a round grain silica sand that has a neutral pH, and onto that silica sand, we place four chemical binder system. One is a shell phenolic system, one is a phenolic urethane cold box system, another is a furan system, and another an alkali isocyanate oil. All of the binders, we chose to put the same total amount of binder, and we kept the sand the same. And I put a note on the bottom. The percent binder is held constant for each chemical binder type to reduce the variability in the experiment. All of the sands were held constant, and so too was the test temperature, head pressure during the test. We just wanted to compare what would happen. Again, this will not be an indictment on any of the chemical binder system. It is to make a point. And the point is, if I show the displacement on the x-axis and time as a function of temperature for a typical axial or longitudinal thermal distortion curve, what you are seeing here for these sand binder systems that I just mentioned, the alkaline isocyanate oil in brown, the furan system in black, the urethane cold box system in yellow, and the shell system in a tan color. These systems, they all show a different shape, and you can see an undulation pattern indicating that there is different thermomechanical, different thermal chemical experiences for these binders. And the thermal distortion curves are almost a signature for the sand binder levels that we are using for a sand type. Certainly, some of this distortion is due to the fact that we are using silica sand, which has a purely expansion type of movement. The expansion is simply the cookie moving away from the hot surface. The plastic movement, when the binder system goes below the origin or when the curves sags down is the cookie sagging around the hot surface of the test apparatus. We measure those changes. So certainly more stable sand systems can help to minimize the distortion problems. And that is the reason some of our foundries have adopted the ceramic sand media to go along with a suitable chemical binder system after qualification regimes and testing. Certainly, I mentioned the ideas of cracking. Here I'm showing you the crack propagation radially, and on the top view of the specimen, here is that crack. We can tell from the thermal distortion where we see this inflection on the curve, the time that that crack occurs. The main thing that we have to understand is not the fact that the specimen can crack, but we need to understand from the simulation activities that we run for our casting simulation when that alloy will skin or when it will freeze relative to the crack propagation. If it freezes, then no problem from the crack, maybe some distortion issues, but ultimately we will not have the problems that could be metal penetration or veining. Those are the important issues. And for that reason, I am suggesting that we must qualify the sand binder system. To share with you some ideas around qualification, here I'm showing you a casting or some types of castings, a rotor, propeller example, where we are using more than a chemically bonded sand. We are using a chemically bonded sand with and without a coating technology, a refractory coating technology to stop this problem. However, if a foundry employs a granular media, such as ceramic sands, they avoid or they try to avoid going to an additive like an engineered sand additive like a refractory coating. Why? They need to answer the question, does the refractory coating technology provide a marginal benefit to the alternative molding media? That's an important question. Why? You're paying more for the marginal benefits of a ceramic sand. Why do we need to apply a refractory coating? That's like a band-aid. Does the band-aid heal the cut? We need to figure this out. And we need to understand the coatings, and better ways to study that is that we can take our cookies, our dish-shaped specimens, and we can coat it. But I can't do this manually. To be sexist, every man shakes differently. If I have to coat it, I have to do this in an automated fashion with a set dip time, with a set number of shake time, and allow it to dry before we can test it. We can look at some of the rheological issues on the coatings, such as the solids, the surface tension, the surface energetics via contact angle. And we have studied these coatings on these chemically bonded sand substrates. Here I'm showing the surface energetics on a finer sand like the 710 on the left versus a coarser sand on the right. For example, the 710 sand would have a 75 to 80 GFN. That's the grain fineness number. And the 430 would be closer to 50, 55 GFN. You can see that the rheological properties from shear and surface energetics, if we measure the contact angles, are quite different. So we understand from doing a test, we can understand other mechanical, physical, and chemical consequences if we are driving the understanding of chemically bonded sand systems through the data analytics. That's important. Certainly the dip time. Here I'm dipping the same sand binder system for 1 second versus 6 seconds. And you can see the difference between the proud coated layer. The proud coated layer is what is nominally above the sand grain versus what has penetrated the sand grain and then the staining from the water. But we need all of this. We need the proud layer to give us the protection. We need the mechanical penetration to interlock with the grain to give us the strength for the coatings. But how much? How much proud coating? Coating is not for free. And then how much penetration? That's a function of dip time. Because if that wet layer goes deeper into the sand binder system, it could potentially weaken that sand binder system in the casting experience. And we have measured the permeability as a function of the coating thickness. So here we are showing the nominal deposits of the coating above the surface, below the surface, and then we measure permeability for these specimens. We can tell that, yes, it's logical. The coating thickness is related to permeability. So for the same sand binder system, we can see how that proud layer or that penetrated layer can retard the venting characteristics of the sand binder system in the casting process. Here we are showing you the pictures. On the top row is showing you an uncoated specimen versus a coated specimen. And if it's a chill coating like this graphite coating that we have used on the bottom, yes, the coating does protect the mold metal interface from veining or penetration. However, because this chill coating allows the heat to penetrate, because we know the heat is penetrating. If you look on the back side of the specimen, we are measuring the temperatures, but you can see the same amount of pyrolysis and you see the crack. So you know the heat is getting through. The coating in this case is protecting the mold metal interface from maybe defects like veining or penetration, but it is not preventing the casting from distortion or displacement. And here, if I blow the coating off that sand on this test specimen, you will see the pyrolyzed sand falling away. We have collected that sand and we have measured the LOI, and we know that there is 40 to 60% of that chemical binder still on that pyrolyzed black sand. It's still there. So the coatings, we have to choose the right solids levels that we place on the sand as well. Here we have blown the coating off with 20 psi pressure, 40 psi pressure, and we have measured again the amount of binder left after thermal experience for a 38% solid and a 42% solid. But when we apply greater solids, that will give us a proud layer. What you see, if you look at the cross section of the field specimen, you see now versus the lower levels of solid, you see a delamination. You see the mold wall dilate. It's the gas from the chemical binder system delaminating against the coating layer. And that is going to cause distortion as well. All of these problems can be depicted from an uncoated and a coated specimen at higher binder levels. So we have to engineer these coatings. They can prevent the veining and penetration. But right now, if we don't choose the coating correctly, they will not prevent distortion. And here we are seeing whether we coat or we don't coat, there is no difference for expansion and plastic deformation for the sand binder systems. Expansion and the plastic deformation. Further on that, we are showing the foundry engineers what they like to see. They know laboratory data is interesting, but it's sometimes irrelevant to them if they don't see the casted surface and know that they can make a usable casting. So from these cookie trials, we will be able to show you if there is the presence of veining, penetration, or any surface roughness. We can measure that. Our casting trial is simple to understand. It works. I'll keep it in food, in the terms of food. It's like a cookie in a donut. And we place these recipes, different recipes, under the same head pressure, under the same metal chemistry, and the same superheat. And we wet them in that relationship. When this particular casting has solidified, we can shake out these castings. Okay, let me show that again. We fill it, and then we would perform the qualification against the chemistry, the superheat, and the head pressure, and then we can do some shakeout analysis. We put a known amount of energetics onto the casting. This is the donut with the cookies in place, and we shake it out. We will know which sand binder systems are easier to shake out, which is less, and we again, from the retained strength, will measure that energy. But when we section that casting at the mold metal interface, relative to the alloys, the ones at the left of this region is iron castings, the one to the right is steel. But we are collecting a database for different binder systems, different interfacial conditions, and measuring the mechanical, thermal, physical, and chemical properties to develop the database for the sand binder systems, whether they be ceramic media, alternative media, specialty media. We are trying to understand this from the sand binder system size, distribution, and variability relative to those conditions. The qualification is a performance predictor. We are seeing that it relates to actual production concerns. And for that reason, we encourage the foundries to qualify a chemically bonded sand system through testing and casting trials in order to prevent issues of defects and process concerns. With those thoughts, I hopefully am within time to entertain your questions. Thank you.